Okay, let's talk about graphing two systems of equations. And a system of equations is just like we were talking about in the intro video, that if we add two numbers, they equal 10, right? If I turn those into variables, just placeholders for the numbers, right? I have one number plus another number is equal to 10. I'm going to make it a little smaller so I can keep everything graphed on the page, but let's do how about 5? So two numbers that add to 5. And I could just put in as a placeholder, variables x and y, right? So x plus y is 5. And then the difference of two numbers was also 10 in our example, but I'll do the difference of two numbers is 5. So if I graph all of the solutions that would make this true, those are points on a graph that would show up as ordered pairs. Okay, pairs of numbers. That's all it is. So if I let's say, okay, say x is 3. What is the y value that makes it true to be 5? So 3 plus 2 would be 5, right? So 3 plus 2. So 3 in the x and 2 in the y would be that point right there. Now I could do what if x was 2 and then y would have to be 3, right? So 2, 3 would be that point right there. I can do 1, 4, so 1, 4, and then 4, 1, and then 0 and 5, right? 0, 5, and 5, 0. And you'll see that all of these solutions end up being on the straight line. And I could even think of like, well, 2.5 and 2.5, right? So 2.5 and 2.5 would be right there between those 2 points. And you could even think of, any decimal point, so maybe 1.3 and so 1.3 and 3.7, right? So 1.3 and 3.7 would be somewhere around there, right? And you could even go in the negative numbers. So how about -1 and 6, right? -1 and 6 would add to 5. So right there. So you could see that all of these solutions to that addition equation would fall on this line that goes like that. Now, how about the difference of two numbers is 5? So how about, 5 for x, right, minus 0 would be a solution, right? 5 for x and 0 for y would be that solution right there. So I actually already know the intersection point's going to be right here. What if it was 1? 1 minus a -6, right? 1 minus a 4, right? 1 minus a -4, minus a minus is then plus, so it would be 5. So 1 minus a -4 would be right there. And 2 minus a -3, right? And then I kind of see the pattern. So 6 minus 1. So 6 for x and 1 for y would be 1.7 minus 2, right? So 7 minus 2 would be 5. Or how about, I don't know, 9 minus 4, right? 9 minus 4 would be up here. And you can see all these points would line on this line right here. So where are the pairs of numbers the same number that result in the same solution? So that's right there, right? So this point right here where x is 5 and y is 0 is that ordered pair. And you can see that every other point you do not get the same ordered pair, right? So this ordered pair is not the same as that ordered pair, and this ordered pair is not the same as that ordered pair. 4, 1, right? It's not the same as 4, -1, right? So these two are different ordered pairs. This is the same ordered pair, and it's a solution to both equations. So what we want to find is the intersection point. Where is the point a solution to one equation, and it's also a solution to the other equation? So let's think about this one. This might be like the percentage of maybe this line represents the percentage of men in the workforce, and this one the percentage of women in the workforce, and maybe this is like 1960, and then over time there's more a higher percentage, and we're getting closer to 50% of the workforce being women, and the percentage of men, well, there might be the same number of men, the percentage is coming down due to the fact that more women are working. So at some point, maybe we can model this as a line. We say, well, at what point, I mean, this is 2010, right? At what point will be an equal number of men and women working in the workforce? So that would be at 50%, right? 50%. So maybe we can model this with lines, and then we can kind of predict using this graph, and we could say, okay, it looks like if this trend continues, we could say, and we can figure out exactly, what the rate of change is over time. Then we can say, okay, at this point in time, these two will have an equal number at 50%. Okay, so that's kind of how these things work. This graph right here, it's easy to see that the intersection point, this is where this line and this line have the same point. So you can estimate that point, and you just look at the x-coordinate. So this is like maybe 1.3, I don't know. And this is negative 2.5. So I would say, I would estimate the solution that this would be the order pair 1.3 comma negative 2.5. So that's how you estimate solutions with graphs. Okay, so when we're given the equations, we can actually graph them and then estimate the solution and then plug them in to see if it's true. Okay, so this one, my starting point is y equals 2. My slope is 1/2, so every one it's going to go up by 1/2. Okay, so if you remember that, or rise over run, up 1/2. So this graphs like that. This one, there is no constant, so it starts at 0. So if x is 0, y is 0, so it goes to the origin. And then the slope is 3/2, so up 3/2. I don't know, it looks like I land right on that point. Or each one it's going up by 3/2, 1.5, right? 1.5. So it's going to be just like that. So I can estimate that the solution would be 2, 3. And now, if I plug those values in, it should make both of the equations true, right? So if I plug in 2 for x, 2 times 3/2 would just be 3, and 3 for y. So that one checks out. So if I say 3 is equal to 3/2 times 2, that is true, isn't it? 2 divided by 2 is 1, so I get 3 equals 3, which is a true statement. And if I plug 2, 3 in for x and y for this equation, so 3 is equal to 1/2 times 2 plus 2. So 2 divided by 2 is 1, so that's 1 plus 2 is 3. So I get 3 equals 3 again, which also checks out. So you can see that the solution, and if I picked any other point on this line, 0, 0 is the solution to this, 0, 0, right? If I put in 0, 0 here, I get 0 equals 0 plus 2. Does 0 equal 2? No. So this is a solution on that line, and it's not the same as the solution on that line when x is equal to 0. What happens when you have two parallel lines? Is there any intersection point? Okay, if you go out to infinity, it will never cross, right? That's the kind of the definition of parallel, that they have no intersection point. So this in a 2D plane, so it has no solution. Those do not cross. Now, what if the line was right on top of another line? So like this was an equation of one line, and then the green is an equation of another line. Then actually all these points are solutions to both the green line and the black line. So this would have all, an infinite number of solutions. So infinity we draw as a sideways 8. Now, do you think it's possible to have exactly two solutions? Right? Is there a way that you can position the line so maybe I put the line so they go way out but don't cross for a long time. would there be two solutions? Or could you have it in such a way that they would cross twice? And really, the answer is no. You cannot have two solutions. You can only have either one ordered pair solution, so one solution, or you could have no solution if their lines are parallel, or you could have an infinite number of solutions if the lines are right on top of each other, right? So if they're right on top of each other, then all the points are solutions that make up those two lines. Okay.